And what I'm about to show you here in this last example from yesterday is really overkill. It's something that we can show, we can use concepts of calculus to find answers to certain problems that we could just answer by looking at the situation without using any advanced math. So generally speaking, it's rational functions that have horizontal asymptotes. There are exceptions to that. Exponential functions do. Excuse me. Exponential functions do. There are other classes of functions that you wouldn't even get close to touching in high school that do. But generally speaking, it's rational functions. Although some functions don't have horizontal asymptotes, the concept of the limit of the function as x approaches infinity or negative infinity still tells you something about the function. It's going to be a bit of a letdown in terms of what it tells you, but let me demonstrate that to you. So what is the limit as x approaches negative infinity of x squared minus x cubed? And by the way, there's a meaning in terms of the graph of this function, but it's also important you understand what we're going to do here because it has other applications. I hope you know that as the math gets more and more advanced, even though we like to use applications, sometimes you're doing math for the sake of doing math. You're doing math in a certain way to prove theorems, which maybe are not applications. So there are other uses for this. How we find this limit is we want to factor the argument of the limit. So this is the limit as x approaches negative infinity. And we can factor this into x squared and 1 minus x. Now, there are x's in all of these factors. And the reason there are x's in all of these factors is the original argument was basically a polynomial expression. So each of these factors is going to be infinite in scope or scale. It may be positive infinity or it may be negative infinity. So we start off with the idea that each of these factors is going to be infinite. As x approaches negative infinity, what will x squared approach? Positive infinity. Because x is getting infinitely large in the negative direction, but we're squaring that negative number. I want to say that again in case I misspoke. X is getting infinitely large in the negative direction, and when we square that negative number, we get a positive infinitely large number. Now, this will also approach positive infinity because you're taking 1 minus a negative infinitely large number. 1 minus negative 5 is positive 6. So as you take 1 and subtract an infinitely large number, you're going to get an infinitely large positive number. So what this is telling you is that this is positive infinity. And your brain probably says, yeah, so what? What is that telling us? What it is telling us is that graphically, if you wrap your head around what x squared minus x cubed means by looking at it pictorially in a graph form, negative infinity for x is over here. So x is approaching negative infinity. Why am I talking about negative infinity when the answer is positive infinity? Because the limit was as x was approaching negative infinity. What is this telling you that the limit is equal to positive infinity? What is that telling you? It's telling you that as you go further to the left, y goes further up. Which is telling you a very uninteresting piece of information. The graph of the function looks like that in that quadrant. That as x goes infinitely to the left, y will go infinitely up. And the reason why we don't really need to do this is if you consider this as a function of y equals x squared minus x cubed, which is y equals negative x cubed plus x squared, it's a polynomial function with an odd degree, which means the two arms are in opposite directions, and the leading coefficient is negative, which means the right arm is down, so the left arm has to be up. It's overkill. You don't need to do that investigation of the function using this idea. But that's what you would do. If, on the other hand, I said, what is the limit of the function x squared minus x cubed as x approaches positive infinity, I would take the x squared out and be left with 1 minus x. And I would say that this is going to be equal to positive infinity multiplied by negative infinity, because 1 minus the positive infinity that x is approaching will be negative infinity. It seems peculiar to be talking about using rules of plus and minus with infinitely large numbers, but it works. And that means that this limit is equal to negative infinity. In my mind, what we're learning in this example 3 is something you will only encounter in one other place in this course. And it's going to be later on in the middle of an example, I think in chapter, doesn't matter, might be chapter 9, where I'll go, oh, by the way, that thing we learned about polynomial functions having limits at infinity that are infinite, we can talk about it there. Let's do one more quick one. What is the limit as x approaches infinity of this expression? Well, as x approaches infinity, the 2x will approach infinity. The 2x does not approach to infinity. I hope you know that infinity doesn't work that way. Alex, can you stop that? It's distracting. Thank you. 1 minus 2x will approach negative infinity because I'm taking 1 and I'm subtracting an infinitely large number, 2 infinities. This next piece will be positive infinity because it contains a factor squared. So 2 minus x will approach negative infinity, but when I square that, it's positive. And then this will be positive infinity for the x minus 1. Because infinity minus 1 is still positive infinity. When you multiply these out, you get a negative, so it's negative infinity. And there's not much to this example. I've, over the years, grappled with, well, maybe just remove it. It's not that important. But you never know when you might see it later, particularly in post-secondary. Any questions from example 3 then? Okay. All right, let's get back to the business at hand, which is the next lesson. I believe this is on page 32 of your unit handout. We're going to learn today about what's important concerning the second derivative. That note at the top is just for me to modify my note package for later, next time I teach this course. We're going to be talking about understanding something first of all and then applying it. We have to understand how the second derivative tells us something about what is called concavity, which is a type of shape or a way to classify a shape of a function. And then we're going to apply that in order to determine where concavity is one type of shape and where concavity is a different type of shape. We're not going to be graphing these functions in the examples today because, think about the examples yesterday when we had all of the intercepts, all of the asymptotes, the max-mins with the first derivative chart, and I gave you the derivative yesterday. Think of how long it took us to do those. So even though I am going to give you the derivative and second derivative today, if we do everything, including the new stuff, we'd be here all afternoon. Okay? So, a background of what's going on here. I have to find my little clicker. We're going to start off with talking about what the derivative of a function means in terms of what the function is doing. If the derivative of a function is positive, then the function is increasing. And I know that's probably obvious, but I want you to roll it around in your head for a second and think about that statement. I could say if the derivative of a function is positive, the slope is positive, but I don't want us going down that road. I want us just saying that the function is increasing. If the derivative of a function is negative, then the function is decreasing. Right? Because the derivative is telling you how the thing is changing. It doesn't matter that we're talking about function here in terms of you understanding the nature of a positive or a negative derivative. What matters is if the derivative of the function is positive, then the function is increasing. So it could be volume. I could be saying the derivative of the volume is positive. Well, that means the volume is increasing. If I say the derivative of the volume is negative, then the volume is decreasing. And we use this idea, and we have used this idea, to find out where volume is max. Because we're interested in where it stops increasing and where it starts decreasing, and that's where the derivative changes from being positive to negative. Right? So again, if the derivative of a thing is positive, that thing is increasing. We could use position. If the derivative of position is increasing, then if the derivative of position is positive, then position is increasing. If the derivative of position is negative, then position is decreasing. This is where the concept of positive velocity and negative velocity comes in. Are you with me here? That what I've got highlighted kind of or indicated in pink could be anything, could be velocity itself. If the derivative of velocity is positive, what is that telling you? It's telling you the velocity is increasing in value. And if it's negative, it's telling you the velocity is decreasing. So now comes the part you really have to think carefully of. That means if the derivative of a function tells you what's happening to the function, the second derivative of a function tells you what's happening to the first derivative of the function. Because the second derivative of a function is the derivative of the function. So, back up here, I could have put, instead of position, I could have put derivative. If the derivative of the derivative is positive, then the derivative is increasing. And I think you're okay with understanding that, but what does that mean? I mean, by way of comparison to what we've said, it makes sense that the derivative of a function being positive means the derivative of the function is increasing. You with me on that? Okay. Well, to paraphrase it in a different way, now I'm going to go back to slope. If the second derivative is positive, it's going to tell us that the slope is increasing, because the second derivative is the derivative of the first derivative. The first derivative is the slope. So the second derivative is the derivative of the slope. And if the derivative of the slope is positive, the slope must be increasing. Okay. And I'm not saying that you should be able to articulate all of this in words on your own or even verbally. I'm saying you should understand how I've come to this conclusion logically. It turns out that shape is called concave up. And that shape will always look something like this. It will look like a happy face, look like a smile. It will look like something that if you put out in the rain, this analogy will break down very shortly, but when you put out in the rain, it will collect the water. It's like a bowl with its open part up. And we say it's concave up. And you can remember that if you like, because if the second derivative is positive, right, I'll use this notation, d2y dx squared is positive. People who are positive, generally speaking, smile. Right? The shape of their mouth has that concave up approach or look. Now, I want to go through this and explain to you why the slope is increasing everywhere. Because I've said, let's go back and dissect this again. If the second derivative is positive, that tells us the first derivative is increasing, which means the slope is increasing. So if I take an arbitrary point, point A, would you agree that if I said the slope of the tangent at A was -3, that's not too far off the mark? You can buy that, depending on how the graph is scaled. Well, if I go to B, would you agree the slope there might only be -2? And then -0.5, 0. These are numbers that hopefully these slopes make sense to you, these numerical values of the slopes. Okay, so going left to right, there's always an increase in the slope. From -3 to -2 is an increase. From -2 to -0.5 is an increase. Right? If I have negative $2,000 in my bank one day, I have more then than I did the previous day when I had -3,000. I still don't have any real money, but you get my drift here. -2 is a larger number than -3. -0.5 is larger than -2. These are all increases. So there's your justification. You know, in the end, what you need to remember is that if the second derivative is positive, it has a concave up shape. That's what you need to remember. I'm trying to explain to you why that's the case. If the second derivative is negative, okay, again, the second derivative is the derivative of the first derivative. The first derivative is the slope. The second derivative then is the derivative of the slope. So if the second derivative is negative, the slope is decreasing. And it turns out that's called concave down, and it will look like this. But maybe not a complete umbrella shape, but I hope you catch my drift that it has that curviness to it. And again, I could pick some arbitrary slopes here. I'll give you a second to ponder those numerical values for each of those 6 points. They should make sense to you. You know, you don't have to get out a ruler and drafting tools and measure stuff. If the slope at A is +3, I think you could buy that the slope at B is maybe only +2.5. But again, going from each of these slopes to the next, left to right, is a decrease in the slope. And, you know, once again, we're talking about the second derivative being negative. People who are negative, and they're all around us, it seems, these days, generally walk around with a scowl on their face. Right? So that's a way to remember, although it's usually not a problem remembering. So what's an inflection point? You don't get into this in Math 20 or Math 30. In Math 30, all you do is you say, that's where the graph comes up through the x-axis and it has that wrinkle or that twist or that kink to it. But if you think about that for a second, I'm not going to draw an axis. If this is an inflection point here, what's happening is it's going from concave down to concave up. This is what an inflection point is. It's where the concavity of the graph switches from one type to the other. So wherever the function changes concavity, we call that an inflection point. At that point, it is neither concave up nor concave down. Because if it were concave up, it wouldn't be an inflection point, right? It's got to switch. However, it doesn't mean the second derivative is 0. It means at that point, the second derivative is not positive, because it's not concave up, and at that point, the second derivative is not negative, because it's not concave down. The second derivative there can be 0 or not defined. Just like if the first derivative is 0 or undefined, the point might be a maximum or a minimum. If the second derivative is 0 or undefined, the point might be an inflection point. Just like every max or min is at a critical value of x for the first derivative, every inflection point will be at a critical value of x for the second derivative. So there's a nice symmetry here to what's going on. Once again, I think you get this, but if the second derivative equals 0, it doesn't mean there's an inflection point there. If the second derivative is undefined, it doesn't mean there's an inflection point. But what it means is it might be an inflection point. How, when we were talking about max-mins and critical points, what primary tool did you use to determine which of the critical points actually corresponded to max-mins? What did you have to do? Who can tell me? Alex? Can you be more specific? The first derivative chart. So here, you're going to have to do a second derivative chart. That's all. So if you want to get a true picture of a graph, you're going to have to do asymptotes, intercepts, symmetry, find the first derivative to find the critical values of that, to find max-mins in a chart, first derivative chart, find the second derivative to do a second derivative chart with its critical values of x to find the inflection points, then you can put it all together and sketch it. The good news is we're not sketching things today. Okay? So let's take a look at the first function. F of x equals x squared plus x over x squared plus 1. And we are asked to determine everything, including inflection points. And I thought I had put these in here because I didn't want to spend class time doing it this semester, but I didn't. So I put them in here, and you're going to take a minute and write down what the first derivative is. And what the second derivative is. Again, sometimes I think it's important, sometimes it's not important, but sometimes I think it's important for students to understand the reasoning behind what they're being taught and what they're doing. We already know how to find the derivative and the second derivative. This is just a time-consuming process. It's going to eat up 20 minutes of our class time. And we're already halfway through class. Okay, so let's write down all of the information that we can. First of all, we have an x-intercept at x equals 0 because we eyeball the numerator of this rational expression and say, oh, if the numerator is 0, the whole thing is 0. The only value of x that makes the numerator 0 is 0. We could, if we want, use a rule for the y-intercept by saying I'm going to put x equals 0 in. But we're back to that, and this happens quite frequently. We're back to that idea that if you have an x-intercept of 0, you also must have a y-intercept of 0. So the fact of the matter is there is passage through the axes in only one place, and it's at the origin. This function is odd, and you know I do not mean peculiar. I mean when I put negative x in, I end up with the negative of the function. I'm going to get negative x on the top over x squared plus 1 on the bottom. It's an odd function, which might be helpful if we're asked to sketch it, and it's definitely going to be helpful as we go along doing other things. That if the function's odd, we better see just as many critical values of x for the derivative to the left of 0 as to the right of 0, and they need to mirror each other. Same with the second derivative. Asymptotes. There's no vertical asymptote. And listen, as much as I started off today by reviewing that whole, we need to find a limit as x approaches infinity, sometimes it's just useful to look at the degree on the top and the degree on the bottom. And if the degree on the top is smaller than the bottom, then y equals 0 is a horizontal asymptote. What does that mean? Well, it means the x-axis is an asymptote. So we've got all that preliminary stuff out of the way. Now what we need to do is a first derivative chart. So wherever you wrote the first derivative, you should indicate that the critical values of the first derivative are 1 and -1. Those are the values of x that make the numerator 0, therefore making the derivative 0, meaning it's critical. There are no critical values of x that make the derivative undefined by looking at the bottom because it's x squared plus 1. While we're here, I guess what we can do is we can write the critical values of x for the second derivative, and they are 0 and plus or minus the square root of 3. Because one of the factors is x squared minus 3. When you set that equal to 0, you get plus or minus root 3. Again, there are no critical values of x associated with the denominator. The critical value of x of 0 is because of the 2x as the factor. Are we all okay with that? No questions? Okay. So let's do a first derivative chart, and I'm just going to freeze this information over here while I write down my table. For the first derivative, I'm going to be going from negative infinity to -1, from -1 to infinity, from -1 to 1, and from 1 to infinity. And across the top, I'm going to put all of my factors. Now, I'm going to choose to put 1 plus x, 1 minus x, because my preference is to use linear factors so I can do that sign change thing. If you want to put 1 minus x squared there as a single factor, you can, but you need to be aware it's going to go from, say, negative to positive to negative. It's going to switch twice because it's quadratic. I also have the x squared plus 1 squared, which will be positive everywhere for so many reasons. Overridingly, if that's a word, the x squared plus 1 is squared. Maybe just as important, x squared plus 1 will never be negative anyway, because x squared will always be 0 or greater than 0. We're also going to put here the second derivative, dy dx, and then what y is doing. So this is a little bit, there's just a little bit of thought here. And you can develop your own strategy. Strangely enough, as soon as it's, I can unfreeze that. Strangely enough, as soon as it's 1 plus x, if it's x plus 1, I have no problem at all knowing exactly what's happening. You write it as 1 plus x, and that just throws my brain into disarray for an instant. This one will be negative, this one will be positive, positive, negative. And I'm not going to spend class time here explaining this to you. You can develop your own strategy. It might be as simple, even though these are linear and they're written backwards, which is what confuses the issue. Even if your strategy is something as simple as putting a number in and seeing if it's positive or negative. That means that the first derivative is negative, then positive, then negative, which means the function is decreasing, then increasing, then decreasing. Which means there is a minimum here and there is a maximum here. Which really makes sense because it's an oddly symmetric function. So if over at -1 there's a minimum, at +1 there has to be a maximum. While we're here, and again, we're not graphing. We're not going to put this all together. I'm going to show you what the graph looks like in the end. And we'll be able to confirm all of the information we found. But let's find the y-coordinate of the point. So we have to go back and look at the function, because I've forgotten what it is. X over x squared plus 1. So when I put in negative 1, I'm going to get negative 1/2. Don't just take my word for it. We're putting negative 1 in for x. I believe we're getting negative 1 over 2. And when I put it in positive 1, of course, I have to get positive 1 over 2. So at negative 1 comma negative 1/2 is a minimum, and at positive 1, positive 1/2 is a maximum. Now what we need to do is find inflection points and talk about the concavity. Once again, I'm just going to freeze my derivatives on the other screen here while I build my table. My critical values of x for the second derivative are negative root 3, 0, then positive root 3, which means I'm going to be slicing up my domain into the interval from negative infinity up to negative root 3, and from negative root 3 up to 0, and from 0 up to root 3, and root 3 up to infinity. It's been a long time since I've said this, but I'll remind you. If the domain of all of the function is all real numbers and you have 3 critical values, then you're slicing that domain in 3 pieces. You should get 4 intervals. Across the top, what we are going to do is we are going to put all of the factors of the second derivative, which are 2x, x squared minus 3, and x squared plus 1 cubed. Make sure I've got them all, and I do. That first row should be easy. When x is negative, 2x will be negative. When x is positive, 2x will be positive. The last row should be easy. Even though the x squared plus 1 is not squared, it's cubed, it's still positive everywhere because x squared plus 1 is going to be positive everywhere. This is going to require more thought. There is a way to reason out what the pattern is going to be, and it's for you to imagine that this is a function. I'm hesitant in putting y, so I won't. H of x. If this is h of x equals x squared minus 3, it's a parabola that opens up. So it looks like this, and where my armpits are the 2 x-intercepts. So that thing will be positive until it hits that x-intercept. It will be negative in between the x-intercepts, and then it will be positive again. If you imagine putting a number in this interval like negative 10, when you square negative 10, you get 100. 100 minus 3 is positive. Same thing over here. But if you put a number, I don't know if this is even worthy of explaining, but I want to see because some of you might understand it. When you put a number between negative root 3 and positive root 3, and you square that, you're going to get a number less than 3. And then when you subtract the 3, you will get a negative. So there's another way that you could reason it out. So what does this tell us? It tells us that the second derivative is negative, then positive, then negative, then positive. What does this tell us about the function? It tells us it's concave down, then concave up, then concave down, then concave up. What does that tell us about this point here? There's an inflection point. There's an inflection point. There's an inflection point. And again, I have kind of a limited amount of space to work with here. I think you have more space on paper. I'm just going to move this over a bit so that I can write what the coordinates are. So we have an inflection point at negative root 3, comma something, at 0, comma 0. I don't even have to think about that because I know it goes through the origin. And an inflection point at positive root 3, comma something. Let me write the function up here. When I put, I'll do the root 3 first. When I put root 3 in for x, I'm going to have root 3 over 4. Because in the denominator of this expression, I'm going to square root 3 to give me 3, plus the 1 is 4. I get root 3 over 4. And then over here, I'll get negative root 3 over 4. And we are done the question. We have come up with all of the important information. The coordinates of the max-mins, the coordinates of the inflection points, the fact that there's a horizontal asymptote, the fact that it's odd. And I've preloaded this function into my calculator. So I will show it to you. So this is what the function looks like. Now, first of all, let's deal with the fact that it goes through the origin. Definitely goes through the origin. Goes through the origin. There is a horizontal asymptote here. I could change the window settings and demonstrate to you that it's continuing to go down. What are the coordinates of this point and this point? Well, let's find out. If I go to my calculate menu and choose max, and scroll to the left of that point and then to the right, I get 1, 0.5. Those were the coordinates of the max. If I do that with the min, same thing. I want now to plot the point or trace the point root 3. We said the graph had an inflection point at root 3, comma root 3 over 4. Am I right? Okay. Before I go on, would you agree that it's concave down here for sure, and it's concave up here for sure? Locating where that changes visually is difficult. If I had to guess, I mean, it's also a pixelated graph, right? I would say around there someplace. There's no way for me to tell the calculator to find the inflection point. I'm just saying, let's plot or trace that. And I was off. Yeah, looking at it, it's still concave down there, someplace about there. But can you confirm on your calculator that if you take the square root of 3 divided by 4, you get 0.4, whatever that is? And I hope you would also agree that it is definitely concave up here and concave down here, so it inflects as it passes through 0 as well. Everything matches. What I left out was finding the derivatives and actually putting it all together. So that's a challenging thing, by the way, putting it all together. Let's try another one. Again, particularly with this one, I've learned in the past that I do not want to spend class time doing the derivative and second derivative. So you're going to take a minute and carefully write down the derivative and the second derivative. And as much as we have computers and the AI technology continues to grow and it's starting to weave its tendrils into math and science more and more, it doesn't matter what kind of technology we have to do math for us. Engineers have to do math on paper. They have to solve problems. They have to know the math in order to solve the problems. Because they're not just given a question they can enter into a calculator or a computer. They're given a problem to solve, so they have to figure out different scenarios. That being said, you know, life's too short. So if I go to Wolfram alpha, I can enter x to the third times x plus 3 to the 2/3, which is the original function. And when I hit equals, now you want to be careful with Wolfram alpha because it will show you a lot of information beyond the math that you would understand, particularly the graphs. Don't look at the graphs because the graphs are often not correct for high school. Okay? They show other things that we don't want to talk about. But one of the things you will find is if you scroll, so that's not what it looks like. Okay? We'll get to what it looks like. Is you will find at some point the derivative. So there's the derivative. So when I figured out the derivatives here, I did it on paper first, but then I thought, oh, let's just check. The nice thing about Wolfram alpha is if you want to know the second derivative, then just click on the first derivative and it enters the first derivative in the search field. And you can find the derivative of that. Now be aware, this says d dx of this, but this is already the first derivative. So it's a very nice way to check things. Okay. All right, so asymptotes, no asymptotes. It's not a rational function. We're not dividing by x anywhere, so there cannot be any vertical asymptotes. And you're not going to get a horizontal asymptote for the same reason. You get horizontal asymptotes in general because you have a function over a function. Since I have x to the third there and x plus 3 to the third, at infinity, this thing is just going to be infinite. Kind of like what we did with example 3 from yesterday. Intercepts. Well, there will be an x-intercept at x equals 0 and at x equals -3. Just looking at the factors, we can see those two factors become 0 at 0 and -3. And the y-intercept is found by putting 0 into the function for x. Or in this particular case, just saying, well, if it goes through x equals 0, it goes through the origin. It is neither odd nor even. If I were to put into that function -x, it is true that the first factor of this function becomes the negative of what it was. This is going to become -1 times x to the third. But this thing is neither the same as what it was, nor is it the opposite of what it was. So there's no symmetry. There are no asymptotes, there's no symmetry. All we have are the intercepts. So now we have to get going with the first and second derivative tables. So I suppose it will be beneficial for us to take a minute and write what the critical values of x are. For the first derivative, it would be -3, -1, and 0. -1 because that makes the first derivative 0. 0 and -3 because those make the first derivative undefined. For my second derivative, the critical values of x For my second derivative, the critical values of x are 0 and -3. -3 and 0. I'll just put them in order. I think what I'm about to tell you is true without exception. If you have a critical value of x for the first derivative, and it happens because that's where the first derivative is not defined, you will have a critical value of x there for the second derivative. If a first derivative is not defined somewhere, how could the second derivative be defined there? Intuitively, that doesn't make sense to me that it could be possible. And I think that's a true statement. I think what I've told you is true. So I'm going to freeze this so we can build the first derivative table together. I need to go from negative infinity, and I'm choosing negative infinity because when you look at the original function, there's no restrictions. There's no square roots. There's no divided by things that are not allowed to be 0. From negative infinity to negative 3. Oh, by the way, you can tell it's not odd or even, right? Look at those critical values of x. There's not a symmetry to them past 0. From negative 3 to negative 1, from negative 1 to 0, and from 0 to infinity. Remember, our goal is not to graph this today. That's not our goal. First derivative, thank you. X plus 1, x to the 2/3, x plus 3 to the 3rd. Is that good, Christy?
Yeah.
Okay. So then dy dx and y. So x plus 1 will be negative until it crosses the threshold at negative 1, where it becomes positive. This will always be positive because the exponent is even. X to the 2/3 means you have to square something at some point. You either square x, then take the cube root, or you take the cube root, then square it. You're going to get positive. X plus 3 to the 3rd means the cube root of x plus 3. When x plus 3 is positive, the cube root will be positive. When x plus 3 is negative, the cube root will be negative. So we can basically say, because this is an odd exponent, we're going to treat this as a linear function. It's going to be negative and then switch to positive. Which means the derivative is positive, the derivative is negative, then it's positive, then it's positive. Which means the function is increasing, then decreasing, then increasing, and continuing to increase. Which means we have a max and a min. While we're here, let's calculate those y coordinates. So we're going to have a max at negative 3 comma something, a min at negative 1 comma something, and the function is that. Can we just get a decimal, please? Oh, well, at negative 3 is easy. It's 0. So we may be able to get away with writing exact values. At negative 1, we will have negative 1 times 2 to the 2/3. We will have negative 1, because negative 1 cubed root is negative 1, times 2 to the 2/3, which is negative cube root of 4. Because 2 squared is 4, and then we take the cube root. Had anybody calculated a decimal value of that? Now, Alex, if you take the cube root of 4 and change the sign, do you get the same number?
I got the same result putting that in and also just typing it in.
Okay, so that's what I want to know, is that my reasoning was right and it's matching yours. And that is approximately equal to negative 1 point, I'm going to say 8.
1.58.
1 point, that's what I meant to say. Negative 1.6, okay. All right, we're done that part. Now we have to do the second derivative. And I just want to make sure, when I did that first derivative chart and I mistakenly wrote the second derivative, I did use the proper critical values of x. Okay. So I only have two critical values of x for my second derivative. It's going to then be negative infinity to negative 3, negative 3 to 0, and 0 to infinity. And now we're going to put the negative 2, the x to the 5/3, the x plus 3 to the 4/3. Double check my critical values of x, double check all of the factors of my second derivative. Looks good. Now, as I was saying before my correction was pointed out, or my mistake was pointed out, some of you may choose to put the negative 2 and the x to the 5/3 together as a single thing. By the way, x is raised to the 5/3. 5 is an odd degree. Doesn't matter what the denominator of that is. You're going to raise x to an odd number and then take a cube root. If x is negative, that will be negative. If x is positive, that will be positive. Using a similar argument, this third factor is going to be positive everywhere because it's raised to an exponent of 4 at some point. Whether you take the cube root first and then raise it to the 4, you'll get a positive. Or if you take raise it to the 4 and then take the cube root, you'll get a positive. So my second derivative is positive, positive, negative, which means my function is concave up, concave up, concave down. Which means there is only one inflection point. The concavity changes from concave up to concave down as it passes through 0, so we have an inflection point at 0, comma, the y coordinate is 0. And we have done the question. The question is done. We've answered all of the questions. We've figured out all of the pertinent features. But I want to show something to you now, just to let you know kind of where we're going. Oops. Can you confirm, looking at your first derivative or the information in your sheet, that the first derivative is critical at negative 3, at negative 1, and at 0? Okay. So it's critical at 0, it's critical at negative 1, it's critical at negative 3. I'm going by memory, so I'm going to ask for your help here. Is it true that the first derivative is positive up to negative 3, then negative up to negative 1, then positive up to 0, and positive afterwards? Okay. What does that tell us? It tells us the function is doing this, then doing this, then doing this, and then doing this. And I think I might have mentioned this before. I do not want to put an arrow here because that's a critical point, right? I want to make sure that you understand that. Okay. Looking at the second derivative, am I right in saying the second derivative had a critical point at negative 3 and at 0? So the second derivative also had a critical value of x here and here. And the second derivative was positive, and then positive, and look where I put this positive. Right on that -1, because that has nothing to do with the second derivative. And then negative. Am I right? Okay. That means that the graph of the function is concave up, then concave up, then concave down. Your job then would be to figure out what it looks like. So we know there's an x-intercept here, right? -3, 0. We know it goes through the origin. We know this is a max. I'm going by memory here. So when you look at your first derivative chart, we had a max at -3. And we know that there was a min at -1. Have we got a y coordinate for that min? I know we do, I just don't remember.
Negative cube root 4.
Negative what?
Cube root of 4.
Negative cube root of 4, which is about -1.58. How could you draw this? I'm going to challenge us today to see if you can figure out. I know we don't have a lot of time, but I think this is where most of the learning happens, is being shown the math. You're still going to have time to some time to practice. But does anybody know how we can draw this? It's got to be concave up here and concave up here and concave down there. But it's got to be increasing up to here and decreasing to here and increasing and increasing. Like, I mean, I think, and concave down here, I think it's pretty clear. I want to get rid of some of this. Maybe not, but I think it's pretty clear that it will look like that. And by the way, do you notice how I didn't do a perfect job, how the slope of the tangent at the origin is almost vertical? It should be vertical because the derivative is not defined there. So it's an infinite slope. But the question is, what the heck is going on over here? It's like that. This is called a cusp. And I have that loaded up as well. And that's what it looks like. I also want to show something to you with this. It looks as though this part of the graph, it looks as though the part of the graph surrounding the origin is on the y-axis, right? It's not. It's infinitely sloped at the origin, but everywhere else it's not. And if I were to go zoom box and just zoom in on a tiny, tiny sliver of this, it still looks like it's on the y-axis. So if I were to zoom in on that, I don't know, really cut it thin. I think you know where this is going. We could be here all day. It's only infinitely sloped right at the origin. That's a difficult thing to wrap your head around. There is always space between the graph and the y-axis except at the origin. Anyway, the big lesson here is, can you find concavity intervals? And that's what you have to practice. When I do this part of the course, I like to always go back to the beginning. Let's do asymptotes, let's do it all. But the questions here are just about finding concavity. So it's the second derivative. Unfortunately, when you do these, you have to find the second derivative, right? Or you're the master of your own learning here, seriously. Or you can use Wolfram alpha to find the second derivative and say to yourself, if I'm ever asked to find it, I know how to. Your decision. Okay? I hope that made sense.